Okay, in this tutorial, I'm going to show you how to do some Monte Carlo simulations in LTspice. Okay, this is a type of simulation where we're going to try to model statistical variation in our components and see what effect that has on the circuits that we're investigating. So we're going to launch LTspice, and we're going to start out with a pretty simple situation, and that is we're going to try to simulate some statistical variation in a resistor and look at its resistance by measuring its current voltage characteristic. So we're going to start out by instancing a resistor, and we're going to need a voltage source to supply, let's say, the input voltage. And we're going to get one other component, which is called an ammeter. Okay, this is going to allow us to probe the current in kind of a nice way. So basically this is like a little current arrow, like you'll see me draw sometimes on the side of a wire or something like that. And I've created a symbol in our symbol set for basically a voltage source of 0 volts, which is why it came up here with a reference designator of V2. And when you click on the voltage source, LTspice will basically report the amount of current flowing through the voltage source. And this was originally the only way that we had of probing the current flowing in the branch of a circuit, was to put a voltage source of 0 volts in series with that branch, or in that branch, and then print the current flowing through that voltage source. But now most modern versions of Spice allow us to probe each terminal of the device and see how much current is flowing into the terminal. I actually find it quite helpful to have these little current arrows in my circuit that I can probe. And so this may seem perverse, but we're going to change the name of this voltage source from V2 to maybe IR. These are just strings, and I can basically make the name of this voltage source anything I want. And so I'm going to actually call it IR for the current flowing through the resistor. And I'm going to change the name of this voltage source to VR, which is going to be the voltage across the resistor. And I'll make the nominal value of this 1 volt. And I'm going to connect the bottom end of the resistor and of my voltage source to ground. And I'm going to connect the top end of my voltage source to this ammeter. And so this is my circuit. The thing I'm going to do here is I'm going to change the value of my resistor as follows. I'm going to actually make this an expression. I'm going to call it a parameter R, which I'll define in a minute with the .param statement, times the quantity 1 plus Gauss of CV, where CV is going to be my coefficient of variation. Now, Gauss is a built-in function in LTspice that basically returns a zero mean random number, probably pseudo-random number, whose standard deviation is the value we pass it as an argument. And so what we're doing here is we're going to have some nominal resistor value, which gets multiplied by a pseudo-random perturbation, which is going to be given by 1 plus some small zero mean Gaussian random variable that will cause some small amount of variation about that nominal resistance value. And if I were to duplicate this resistor, that definition of R would come along for the ride. And I could make all of my resistors, if they were all sort of unit resistors with the same nominal value, I can have them all be sort of independent random variables because each time the simulation is run, it's going to define each one in terms of an independent call to this Gauss function. Okay, so in this case, I only have the one resistor in my circuit, so I don't need more than one. So I'm going to need to put in some spice directives. Of course, there's .include engr2420.sub, which we always need. And then we're going to have one that defines a parameter, or two parameters. There's R, and let's make the nominal value of R 10K. And let's make our CV equal to 0.2%. So that represents the standard deviation normalized by the mean, and that's going to be 0.2%, which, as we showed from David Jones' measurements, isn't a bad sort of estimate for a 1% metal film resistor. It's also not bad for the types of Bourne's thick film resistor arrays that we would have used for Lab 1 had we been doing it in class in hardware. So we're going to do that, and now we are going to define our simulation command. We want to do a DC sweep, and we're going to sweep the voltage across the resistor in a linear sweep, and we're going to use 0 to 5 in 50 millivolt increments as well. And it's actually gone ahead and run the simulation. And if you click on this voltage, or if you were to click on a node, you'll notice that's a voltage probe. But if you move over to this ammeter, you'll notice the voltage probe changes into a current probe. If I click on it, I get the amount of current flowing through my resistor. Now for a 100K or for a 10K resistor, if I have 1 volt across 10K, that gives me 1/10 of a milliamp or 100 microamps, which is exactly what we should see here. 5 volts gives me half a milliamp. So it's all working quite nicely. But what I'd like to do is I'd like to actually run a whole batch of these simulations and have each one be done with a different resistor value taken from this normal distribution. So I'm going to just move this down a little bit here, and I'm going to put a dot step in to perform a batch of simulations. So dot step param, and the thing I'm going to step here is a parameter I'm going to call run, which is just the running, like an index of the number of runs that I've done. So I'm going to change that linearly from 1 to, let's say, 500 steps of 1. So like I said, this is just a running index of the simulation number, if you like. And if I click on the little running person icon up here, you'll see that it's actually doing 500 simulations, and it's actually finished with all of them. And you can see that there's a bunch of lines here. And if I zoom in on this plot, you can see that this plot is a bunch of different lines with slightly different slopes. Not a whole lot different, but slightly different. And so what we're going to do is we're going to export all 500 simulations into MATLAB and read them all into MATLAB, write a little for loop that basically goes through and extracts the resistance of each of those 500 curves, and then we'll make a histogram of the results and look at the coefficient of variation for the extracted resistance values. So just like we did in the last tutorial, we're going to export this data as a text file, and actually let me save this schematic as something like a resistor instead of draft 1. Save as resistor. Okay, and let me rerun it. And now we're going to export the data to resistor.txt. So we're going to run MATLAB. Actually, I need to move that file over into my MATLAB folder. So documents, LTspice, resistor.txt into my MATLAB folder, run MATLAB. We'll do LTspice, resistor.txt. It actually takes LTspice longer to parse the text file than it does LTspice to actually run all 500 simulations. Which is kind of sad, but it won't take too long. So you can see in our workspace here we have a variable IR, which is the current flowing through the resistor, and it's a matrix of 500 rows by 101 columns. So each row represents a different run in our batch of simulations, each one for a different resistor value. And then VR is the voltage across the resistor that we swept. And so if we like, we can plot VR comma IR, and a figure window should pop up, and you can see that, oh, where'd my figure window go? You can see slightly variable slope here, just like we had over in LTspice. And so we can use line fit to actually do a linear regression fit to these curves. We'll test that out. So if we go first, last, MBN equals line fit, and we'll do VRIR. We'll do the first row, 1, comma, colon, and we'll use an epsilon of maybe 1e minus 4, and we'll see what we get. Okay, the slope, roughly 100 microsiemens, or micromos, which is about right. Looks like it used all of the points, so that's looking good. So what I'm going to do is define a vector, which I will call R, which is just empty. And then I'm going to do for I equals 1 to 500. And I'm going to just do this first, last thing. First, last, M, B, N equals line fit VR. And then the Y value is going to be IR, the ith row of the matrix, all the columns. Let's see. And I want the same epsilon, let's say 1e minus 4, since that seemed to work out well. And now I'm going to take R and append to it whatever 1 over m was, because the slope of the IV plot is the conductance, and I'm interested in the resistance. So I'm going to take the reciprocal of m, the slope of my best fit line, and just like that, it's done, and we have 1 by 500 vector called R, and we can do a histogram of R, and we can see we have something that's, kind of a roughly bell-shaped curve here with 10,000, 10K right in the middle of our distribution. So that looks pretty good, at least it's believable. And if we go out here and we calculate the coefficient of variation, which is the standard deviation of R divided by the mean of R, lo and behold, we get 0.002, which is the coefficient of variation that we actually put into the simulation. So that's at least comforting. Okay, so that's how you would do a Monte Carlo simulation of just a simple resistor IV curve. Let's do something a little more interesting, maybe. Close down MATLAB. Get rid of draft 1. Let's go back to our non-inverting amplifier example. Oops. I didn't want to open it with LTspice 4. I want to open it with LTspice XVII, which is this one. Okay. And what I'm going to do is I'm going to save this as non-inverting amp Monte Carlo. This is just so I don't have to redraw the schematic. Okay, I'm going to delete the step. I'm going to keep my parameter definition, and this DC sweep simulation command will be fine. What I'm going to do is I'm going to define a new parameter along with R. I'm going to call it again CV, and we're going to make that 0.002, just like before. And we're going to define these two resistors both in terms of a tolerance. And what I'm going to do with R1 is I'm going to make the gain not 2, but maybe 3. And so that means I want the nominal value of R1 to be twice the nominal value of R2. And so I'm going to do that by putting 2 times R times 1 plus Gauss of CV. And then we're going to make R2 just R times 1 plus Gauss of CV. And let's just save that and run it, and let's see what we get. So if we click on Vout, this should have a gain nominally of 3, 1 plus R1 over R2, and yea verily, the ref is at 2.5, so at 2.5 on the input, we should get 2.5 on the output, which is exactly what we see. And then the slope should be 3, so we go over 1 grid line, which is a half a volt, and we go up by 3 grid lines, roughly, which is 1.5 volts, so that's looking good. So now to do a batch of 500 simulations, we need to put in our .step command like we had before. So we're going to do .step param run 1 to 500 in increments of 1. And let's zoom in on that. Come on. This touchpad is killing me. Let me just pick this up and move it a little bit here. Not that it really matters. There we go. Alright, click on the little running person, and it's running through all 500 simulations. And it's done. So if we go up here, we can zoom in and see, yea, verily, there are lots of different voltage transfer characteristics here with slightly different slopes. And so if we zoom back out, we can export this data as well. And let's just click on Save for good measure here. There's our non-inverting amp Monte Carlo.txt. We can move this to the MATLAB folder. And I should have just lowered MATLAB instead of quitting it. Okay. So first order of business is to load spice. It was noninv Monte Carlo dot text. And again, it takes longer to load the data into MATLAB than it does to actually do all the simulations. But there we are. Again, we have V-in, our input voltage, 101 points, and we have V-out as a 500 by 101 matrix where each row is a different run in the simulation. So we can plot V-in, V-out. Oop. They're both lowercase. And there it is. So now we can do the same kind of thing we did before. I would do a test run of line fit. First, last, M, B, N equals line fit, V in, V out, 1, comma, colon, to get the first row, and we'll use 1e minus 4 for epsilon. That seemed to be good. And we're picking out the 35th point to the 69th point, so we got 35 points, and the slope of the line, which is the gain of our amplifier, is like 2.9798, which is pretty close to the nominal value of 3. Okay, so that looks good. So let's make a vector that we're going to stuff the gains in. We'll call it, oh, I don't know, gains. It's an empty vector, and we're going to do for I equals 1 to 500. And we're going to do this first, last, M, B, N equals line fit, V in, comma, V out of I, comma, colon. And we're going to use 1e minus 4 for epsilon. And then we're going to take gains and let that be equal to gains with M appended. And just like that, we have our gains. And so we can do a histogram of gains and see what that looks like. So it looks like the mean value, or the most probable value here, is a little bit shy of 3. So the gain is systematically lower than 3, about 2.97 or so. And we've got roughly a bell-shaped curve here. And so we're going to look at the coefficient of variation of that by taking the standard deviation of gains divided by the mean of gains, and that's 0.0015. Now, what should it be based on our analysis from class this week? Okay, so the sensitivity for the non-inverting amplifier to each of the two resistors, the absolute value of it, or the was A minus 1 over A, where A was the gain. So for the gain of 3, that would be 2/3. So we're interested in computing the square root of the square of the sensitivity with respect to R2, which would be 2/3 squared times the square of the coefficient of variation in R1 squared plus 2/3 squared times the coefficient of variation of R2 squared. And that should be 0.0019. Yeah, 0.0015 and 0.0019 are pretty close. So I'm going to call that a win. And that's it for this. So for Lab 1, we're going to ask you to do basically one of your simulations of the 3 experiments using this kind of Monte Carlo idea. And you'll have to make a histogram of the parameter that you're extracting, which will be something like the voltage divider ratio or something like that. And that'll be part of the Lab 1 assignment. But that's it for now. Thanks for watching.